Alright, we're going to look at a couple other examples of static equilibrium problems that come up pretty often. Now I think the most foolish thing you guys could do is to write down the formulas that I'm creating here and think that you can apply them to other problems. These problems have an infinite variety of manifestations, which means you have to learn the process of creating these formulas for yourself. It's really, really important that you do that. The first type of problem we're going to look at is what I call a flagpole problem. Imagine you have a wall and you got a pole sticking out from the end, and I don't know why I'm calling it a flagpole problem, because I'm going to actually hang a sign from it. Here's a sign. It's a butcher's shop. I'm going to support this pole by a cable that connects to the wall. Typical question that might come up in this problem is, what are the forces being exerted by the wall on this pole? And you got to be careful because there's more than one force here. Well, actually, there is one net force, but in a situation like this, you're very likely to have a horizontal component of that force and a vertical component of that force. So we'll call that Fx and Fy. Now, that's not the only type of problem you can do, but this is just a generic, typical example. This cable that we have is going to make some angle theta with the pole itself. Some of the other things I may need to know in order to do this problem might be the mass of the pole and the mass of the sign. Okay, so let's assume that we know all those things. In order to do this, I'm going to draw a separate free body diagram over here and start labeling forces. So one of the forces I have is that X force that's being exerted the wall. Another force is the Y force that's being exerted by the wall. Now the pole itself is going to have weight. So I'm going to write MPG for that. And the sign is also going to exert a force on the pole. So I'm going to write MSG. And finally, we have the tension being exerted by the cable, which is at this angle here. What we learned a long, long time ago when we were doing equilibrium problems is that an angled force is no bueno. We have to find components of this. So I'm going to draw a Ty component and a Tx component. And I'm also going to recognize that this angle here is equal to this angle here. I can say that Tx is t times the cosine of that angle, and Ty is t times the sine of that angle. A lot of forces here. These can get kind of complicated. If we analyze this in terms of static equilibrium, unlike the other problems we did, not only do we have vertical forces, but we have horizontal forces. We are actually going to have to use Newton's laws in both dimensions. So let's start off with the x dimension. The beautiful thing about static problems is there's never acceleration. So we can just write sum of the forces in the x direction is equal to 0. And now we're just going to substitute. All the right forces minus all the left forces equals 0. So I have Fx is to the right, and I have t cosine of theta to the left, which adds up to 0. This is my first equation. My second equation is going to be sum of the forces in the y direction. In this case, all the ups minus the downs equals 0. So I have Fy, which is up. I have t sine of theta, which is up, minus MPG minus MSG equals 0. That's my second equation. Now the third one is going to be the trickiest one of all because it's going to be the torque equation. The net torque equals 0. And once again, I get to pick the place that's the axis of rotation. Now the thing that's important here is any force that acts at the axis of rotation cannot possibly produce torque. It's like pushing on the hinges of a door. It's not going to produce torque. So I can be clever here and eliminate variables from my equation by strategically putting the axis of rotation in a place that eliminates the most unknowns. In this case, the unknowns in the equation are those forces done by the wall. So it makes perfect sense to call that the axis of rotation because now Fy and Fx cannot possibly exert torque here. But I do have some forces that can. The weight of the pole, the weight of the sign, and the tension. The weight of the pole and the sign are clockwise torques, and the weight of the sign, and the tension is going to be a counterclockwise torque. Another piece of information that we'd absolutely have to do this is how far out are these forces. The pole is easy. If I knew the length of this pole, the center of mass of a pole is going to be in the center. So I could just write 1/2 the length. But I'm not going to do that. I'm just going to actually call this, say, R1 from here to here. And I'm going to call the other distance R2. Remember, all these R's are always measured from the axis of rotation. So my torque being created by the mass of the pole is going to be mpg times R1. The torque being created by the weight of the sign is msg times R2. The counterclockwise torque, which is created by the tension, is going to be T times the length of the pole, because it's out at the end, times the sine of that angle. And that's all going to be equal to 0. If we know all this information out here, it looks like the only unknown in this problem would be the tension, and you can solve for the tension. Once you have the tension, you can go up here and solve for Fx, and then you can also go over and solve for Fy. Now, you guys, again, there's a million varieties of this. I don't have to attach that cable to the end. I could attach the cable here, and then I would have a different angle, I would have a different distance, it wouldn't be L anymore, but that distance would have to be given. These problems can be very complicated because we can make a million variations on it. Another variation of this that you could do is to make the pole attached at an angle. Let's say it's holding up a lamp, and now we've got something like this. The difference here is you're going to have to know the angle that the pole makes with the wall. You're also going to have to know the angle that the cord makes with the pole. This one would be very, very complicated, but it's still doable. And you may or may not see one of those on your worksheet.